All right, so we have our roots chart out, we have our notes out, we are on section 6.2. We are going to be simplifying radicals with larger indexes, okay? Up to this point, we have, in fact, if you guys remember way back to first semester, we have simplified radicals that were square roots. Okay, we did that when we worked with the quadratic formula, we completed the square, all that kind of stuff. We simplified those radicals. For example, if we had the square root of 50, way back when we said, well, we can simplify the square root of 50 by simply saying that this is the square root of 25 times the square root of 2. And so therefore our answer is 5 square root 2. Okay, remember doing that? Okay, well, it's the exact same process with higher indexes. Okay, we've got to know a couple of things. We've got to remember that we are able to do, what they're talking about here is this rule. We had a rule that said a times b to the n power was a to the n, b to the n. Okay, well really all we're doing is that rule backwards here. They're saying if we have 2 squared times 3 squared, that's 2 times 3 squared. So they're saying we have this, we can work it backwards. Okay, if we have 4 cubed times 5 cubed, we have 4 times 5 cubed. Again, we're working this backwards. Now we might want to do that in different situations because it might just be easier. Maybe you don't have a calculator. So maybe I don't want to take 4 cubed and then 5 cubed and then try to multiply those two numbers together. It might be easier, for example, in this case, to take 4 times 5 and get 20, and then take 20 cubed. Because 20 cubed, I can figure that one out pretty easily because I know that 2 cubed is 8. Right? And if I have 20 times 20 times 20, there's 3 zeros. That means my answer must be 8,000. Okay? So I can do that in my head using these types of strategies. Okay, so don't forget the rules. They are there for a reason. That's why we learn them, not just because I say so. Okay? All right, so if we have, just like here where we have the same exponent, we have the same exponent, so we're able just to multiply the stuff inside using this rule. We can do the same thing with roots. Okay, if we have the same index, I can multiply the stuff inside. Okay, that is essentially what we did here. These have the exact same index. It's the square root of 25 times the square root of 2, and so therefore I would be able to write it as the square root of 50. Of course, that's not the way we wanted to work it. We wanted to pull it apart, but we can do that. Okay, if they have different indexes, if it's the square root of 4 times the cubic root of 9, you can't multiply those together on their own. You'd have to simplify it down first, okay? We can actually multiply the stuff under the radicals if they have the same index. If they have different indexes, we cannot. For example, if we take a look at the cubic root of 6 times the square root of 2, they have different indexes. There's nothing we can do about that. I can't reduce the square root of 6, I can't reduce the square root of 2, and I can't combine them because they have different indexes. So, cannot multiply. Okay, because it doesn't have the same index. Now, the second part, part B, we can multiply those. We can combine those two roots because they're both cubic roots. So I can go ahead and say that I have the cubic root of negative 4 times 2. Okay, well, what is negative 4 times 2? Negative 8. So we have the cubic root of negative 8. And what is the cubic root of negative 8? Negative 2. Okay, so that's kind of showing the power of doing this is that, you know, I can't take the cubic root of negative 4 in my head. I could find a decimal of it on my calculator, but I can't do it in my head. I can't take the cubic root of 2 in my head. But if I multiply these two together using my properties, I can actually find the answer, okay, fairly easily. All right? So questions on when you can combine versus when you cannot combine radicals. When multiplying, I mean. You can multiply two radicals together if they have the same index. Okay? If they have different indexes, you can't combine them. You would have to leave this, if this was a part of a problem, you would have to leave part A written that way. You wouldn't be able to combine them. You have to just write them separately like that. Okay? So let's talk about simplifying radicals with larger indexes. Okay, so this rule we have dealt with in the past. Okay, that's how we simplified square roots. We always said that the square root of a times b was just the square root of a times the square root of b. And now we're just using that rule, well, it doesn't matter, forwards or backwards. It's the same rule, right? But now we're using the rule with higher indexes. It's to the nth root, not just square roots. Okay? So we can do cubic roots, fourth roots, fifth roots, sixth roots, forever and ever and ever. 27th roots, okay? We can do all that. We are going to consider a radical simplified if the radicand, now remember, which part of a radical is the radicand? The underneath, the inside the radical sign, right? So that's the radicand. If the radicand has a perfect nth root as one of its factors, then it's not considered simplified. You'd have to simplify it farther. Okay? So what do I mean by that? Look at our two examples. We have the square root of 24 and the cubic root of 24. So the square root of 24, the index is what? 2. On a square root, the index is 2. And so 24 has a perfect square root within it. Okay? One of its factors is 4. 4 is a perfect square. And so 4 times 6 is what 24 can break into. And so therefore, I can take the square root of 4, gives me 2. And the square root of 6, I can't do anything with it, so it stays the square root of 6. I really wouldn't show this work in here myself. Okay? There's nothing wrong with what the book is doing there. It's just that's not how I'm necessarily going to show the work. All right, so the square root of 4 is 2. The square root of 6 just has to stay the square root of 6. And so that's how we have it simplified. We can do the same thing with cubic roots. The cubic root of 24. But you got to be careful because we're now dealing with cubic roots. Okay, and so therefore we're no longer looking for square roots that go into 24. We're looking for cubic roots. And the one that goes into 24 is 8. So 8 times 3 is 24. And so therefore, again, looking at your chart, we are now taking the cubic root. We're taking the cubic root of 8, which is 2. And we are left with the cubic root of 3, which we can't do anything with it, so it stays cubic root of 3. The biggest issue you're going to run into today is paying attention to those details, knowing which root you're dealing with, and then knowing how to find that on your chart. Okay? Because, for example, 64, you guys all look at your charts. 64 shows up on your chart in multiple places. The number 64 does. You've got to know, are you looking for the square root of 64? Or are you looking for the cubic root? I was going to say it's not a fourth root, but are you looking for the cubic root of 64? Okay, and you got to know then how to read that and which one you're actually looking for. Okay? All right, so let's do an example here before we take too many questions. So over to the side, we want to know what is the simplest form of the cubic root of 54x to the 5th power. So we first want to look at that number, 54. Is 54 a perfect, what root? What root are we looking for? Cubic roots, right? That's our index. So we're looking at the cubic root column in our chart. So everybody, that's the only one we're looking for is the cubic root column. Everybody look at the cubic root column. Is 54 on there? No. Bummer. Okay. Well, do any of those numbers that are on that chart go into 54 evenly? Say again? 27 times what? 2, exactly. So we can rewrite this as the cubic root of 27 times 2. Why are we doing that? Because 27 is a perfect cube. Okay, 27 is on the chart. 27 is a perfect cube. And 27 times 2 gives me 54. Well, then let's take a look at the x to the 5th. Is x to the 5th a perfect cubic root? How do I know? This is what we did last week, remember? Simplifying these down, we said the shortcut for doing this was take the exponent, divide it by the index, right? So can I take 5 divided by 3 evenly? No, I can't. So therefore, x to the 5th is not a perfect third root. Okay? But what is the biggest number, smaller than 5, that is divisible by 3? 1's not divisible by 3. But 3 is divisible by 3. Okay? So what we're going to do then is we want to use our rule. Remember, our rules of exponents. We had a rule that says a to the m power times a to the n power was a to the mn power. Okay? That's the product of powers rule. And we're using that rule right now because we basically are given x to the 5th power. I want to break that apart into x to the 3rd power times x squared. Okay? Because x to the 3rd power is a perfect cubic root. Catch what I'm saying? Everybody picking up on what I'm doing? So then I have x cubed times x squared. Now, if I multiplied all my radicand together, I would get that 54x to the 5th. But of course, I don't want to right now. We're simplifying it. Okay, we're taking it out of the radical. So what I want to do now is I want to actually take the cubic root of 27. What do I get? Look at your chart if you don't know. What's the cubic root of 27? 3. What is the cubic root of x cubed? Just x. Oops, wrong color. It's x. And so then we are left with, inside our radical, 2x squared. All right, let's try another one. Right below this, we have the cubic root of 128, x to the 7th. So, first off, we got to deal with that number. We are working with cubic roots. And so you need to look at your cubic root column on your chart. 128 is not on that list. But do any of those numbers go into 128 evenly? 64 times what is 128? 64 times 2. 64 times 2. Okay. Well, now we got to deal with the x to the 7th. X to the 7th is currently not a perfect cubic root. So I want to factor it out. I want to make it into x to some power times x to some power. Okay? But what are the powers? So I look at the 7, I look at that exponent of 7, and I say, what number less than 7 is divisible by 3? And I want the biggest one. The biggest number less than 7 that's divisible by 3. 6. So I have x to the 6th times x to the 1st. Okay? All right, so next we need to take the cubic roots. So the cubic root of 64 is what? Look at the chart. Say it again, please. 4, yes. The cubic root of 64 is 4. What is the cubic root of x to the 6th power? X squared. X squared. And now we are still left with a cubic root. So I have the cubic root of 2x left inside. Okay, let's take a look at another example. Simplifying a product. Please remember, product means multiplication. So we are simplifying a product of two square roots. There are really two ways of going about doing this type of problem. Okay? And those two ways, there's probably more than two ways actually, but the two ways that I would think of is that we could either simplify both radical first, then multiply them together, and simplify that answer. Or we could try to multiply them together first, and then simplify that answer. You guys catch the difference of what I'm saying? Does anybody have a preference of which way we try first? I can try them both if you want, but anybody have a preference of which way they like to go about this problem? Simplify first, then multiply? Okay, let's try that. So, taking a look at this, we want to try to simplify both radicals first, then we're going to multiply them. So, taking a look at our first radical, the square root of 72 x to the third power y squared. Our index is 2, so we're dealing with square roots, so please only pay attention to the square root column of your chart.
There is 72.
Okay, so 72 is not on that list, but do any of those numbers go into 72 evenly?
36.
36 times what?
2.
2. So 36 times 2 gives me 72. How about x to the third power? Is that a perfect square root?
No.
No. So what do I do?
You have to do with x to
Break it
and then
X squared times X.
X to the
Second.
second power times x. Please remember, because x squared is a perfect square. Okay, so that's why we picked x squared and then x. So how about y squared? Is y squared a perfect square?
Yeah.
Absolutely it is. So we just leave it the way it is. Y squared. All right, I'm just going to continue simplifying this first one. So what is the square root of 36? 6. What is the square root of x squared? X. What is the square root of y squared? Y. We are then left with the square root of 2x. Now please notice when I'm doing that, I am only really taking the square root of my perfect squares. That whole first step was to isolate perfect squares, to factor out perfect squares from that radicand so that we can do this. Okay? Anything that didn't have a perfect square as a factor then has to stay inside the radical. Okay, so we're halfway done, kind of. Now we've got to try the other one. We are multiplying by the square root of 10xy cubed. So, is there a perfect square that we can factor out of 10?
No.
No. Is there anything we can do with the x? No. Is there anything we can do with the y cubed?
Yes.
Y to the second times y. Y squared times y. So then the only perfect square that's in that radicand
Is the y squared.
is the y squared. So y square root of 10xy. All right, so we have simplified both square roots. Now we need to actually multiply them together. Okay? And please remember that everything listed here is multiplication. There is no addition, there is no subtraction, so therefore there should never be any kind of distributive property going on here. Okay? The distributive property is only there when you have some number times addition or subtraction of two numbers, right? That's when we use the distributive property. We do not have that. Everything here is multiplication. So because everything here is multiplication, I can really only take the y times y, which gives me what? So I have 6x y squared, and I can multiply my square root times my other square root, y. Why can I multiply those two together?
They have the same bracket.
Because they're the same index. because they had the same index. Think back to that very first example we worked. We said we couldn't do that one, right? That's clear up here. There it is. We couldn't do that first example because they had different indexes. Okay? If they have different indexes, you can't multiply them. Ours, thankfully, has the same index. And so we are able to multiply those. So that means I have the square root of 2x times 10xy.
20x squared y.
Okay, so you're telling me it's 20x squared y. All right, so 6xy squared times the square root of 20x squared y. Great, except I believe that can be simplified. Is there a perfect square that we can factor out of 20?
Yeah, I don't think so.
So yes, we can actually factor out a 4. We have 6xy squared times the square root of 4 times 5. Well, how about x squared? Is that already a perfect square? Yes, it is. And how about y? Can we do anything with y? Y stays y. We can't do anything with it. So our only perfect squares that we can worry about right now are the 4 and the x squared. So we have 6xy squared times, what are we taking out of that square root? 2x. And then what's still inside the square root? 5y. So we can then take 6 times 2 and x times x gives us 12. X squared, y squared times the square root of 5y. Your other option on this problem would have been to multiply our radicands together at the beginning. And we would have said then that we have the square root of 72x cubed y squared times 10 xy cubed. And so then, yeah, it's 720 x to the 4th, y to the 5th. And then we would simplify it down from there. Okay? So the issue there is, of course, that we're dealing with larger numbers. Okay? Working with the variables ends up being kind of easier, I think, but the number ends up being larger. Okay? Any questions? Then I would actually like to work the second problem, the next example, in that way. I want to multiply them together first, then simplify. Just to show you the process. Okay? You get to choose which way you prefer. Because they're both correct, and it's really your preference as far as which way you want to work these problems. Okay? So, in this case, I would rather multiply first. Now, if you are probably already noticing that this one is not as easy to multiply together as the last one was. I mean, 72 times 10 is pretty easy to do in your head. But 45 times 35 is not. So, how are we going to go about this? Well, first off, let's just write them together as the radicand. So 45 x to the 5th y cubed times 35 x y to the 4th. Okay? The next step in the process is I would start simplifying down as far as I can. For example, 45. Is there a perfect square that I can factor out of 45? 9. 9 times what? 9 times 5. So I'm going to go ahead and say that I have 9 times 5 times, and I'm going to leave the x to the 5th at the moment. Okay? And I'm going to leave the y. I'm going to leave my variables. Let's look over at the 35. Let's go to the 35. So 35. Is there a perfect square that can be factored out of 35? Okay, 7 and 5 is the only way it factors. Neither of those are perfect squares. But yes, 7 and 5 is the only way it factors, and notice we already have a 5 here. So I do want to write it as 7 times 5. That's 35. And then what is x to the 5th power times x? X to the 5th power times x is x to the 6th power. And we need x to the 3rd power times x to the 4th power. I'm sorry, y. Yes, y to the 3rd, y to the 4th is y to the 7th power. All right, so we are here. We're here. We want to now start really looking for perfect squares. We already have one. We already have the 9. So I have 9 times, exactly, 5 and 5 is 25, so we have a second perfect square already. And 7 is a prime number, so there's nothing we can do with it. It just stays 7. So we have dealt with multiplying 45 times 35 and reducing without actually having to multiply 45 and 35. Catch what I'm saying? Work with the smaller numbers. Work with the smaller numbers. Okay, let's see, what else here? We can go through and take x to the 6th. Is x to the 6th the perfect square root? Be careful. Don't look at your roots chart. Don't say, is 6 on the perfect squares? That's not what I'm asking. Remember, to simplify variables raised to exponents, when we have radicals, we take the exponent divided by the index. So what I'm really asking, if I'm asking is x to the 6th the perfect square root, what I'm really asking you is 6 divisible by 2? Yes. And yes, it is. So we leave it as x to the 6th. Okay? And so now, again, remember that phrasing. If I ask you, is y to the 7th a perfect square root, I'm asking you, is 7 divisible by 2? No, it's not. But we can break it apart, right? We can break it into a perfect square root times something else. So I'm going to say y to some power times y. So now, what is the largest number smaller than 7 that is divisible by 2? 6. So y to the 7th can be factored into y to the 6th times 1. I'm sorry, y to the 6th times y. Y to the 1st. Okay? So we now have this. Now we can go through and actually take the square root of our perfect squares. There are 4 of them. So what is the square root of 9? What is the square root of 25? What is the square root of x to the 6th power? Say it loud and proud. X to the 3rd. And what is the square root of y to the 6th power? Y to the 3rd. And we are left with then a square root of 7y. Okay, so the last thing we need to do to write our final answer is you need to multiply 3 times 5. So we get 15 x cubed y cubed times the square root of 7y.